Hello and welcome to Down to Earth with Terry Virch, where we talk about what matters down here on planet Earth. If you love the podcast, please subscribe and give us a rating. Today, I'm super excited. We're going to continue our series that we've been doing with Jim Head, but we also have an extra guest. So Dr. Jim Head is a professor of planetary geosciences at Brown University, and future Dr. Erica Nathan is a PhD candidate also at Brown. And she's focusing on the icy satellites of the outer planets. So today we're going to move from the moon and Mars and Venus and Jupiter, or we're moving out to the outer planets. And so Erica, welcome. And Jim, welcome back.
Thank you.
Thank you so much.
So where should we pick up? Should we pick up with the planets or with the moons? I'll let Professor Head kick things off.
Profess, yes, as it were.
Profess, exactly.
No, I think it's really important to think about the differences between the terrestrial or Earth-like planets, the inner planets, and the outer planets and their satellite systems. I mean, I've been interested in the outer planets and satellites for decades. Of course, most of the big planets, the outer planets, the gas giants, don't have a lot of geology, okay, because it's all atmospheres. But the satellite systems are absolutely intriguing because, in principle, they may represent small solar systems. Like, okay, so the sun and the planets, okay, then think Jupiter and this whole ring of satellites extending it away. Was that a miniature solar system? And Saturn and, Uranus, what's that all about? So are these other examples of other solar systems right in our own solar system? This is pre-exoplanet, maybe we could get some different views of how these solar systems form by looking at these satellites arrayed around the gas giants. And so that's been a major, and then of course they're like, it's like a cornucopia or a menagerie of small planets. Erica will talk about this. I mean, they're just incredibly diverse. And so they give us all kinds of examples. Oh, let's make something that's, just a tiny fraction of the diameter of the Earth. And oh, let's make it out of ice and see what happens. You know what I mean? It's like you got this big giant experiment out there. And so when we do that, we see, a lot of things like planetary interactions. What's going on here? You look at, there's this one here. Sorry, folks. Look at this orange. This is Io. It's like incredible. It's all volcanoes, and they're all active. Not all active, but
right,
as we observe them. What's that all about?
I remember that picture that Voyager sent back.
Yeah, absolutely.
That was so cool.
Absolutely.
Like I remember that picture as a kid. Yeah.
And so that's really it's like tidal kneading. You take a planet and you squeeze it, heats it up on the inside. What do you get? Volcanic activity. And then there's ice, the Europa, it's all cracked, it's all broken. And then some of them, wow, what is this tiny one doing here? Well, it was captured. So we study planetary capture, and then we can study their evolution. This is what Erica has really been interested in, is how if you have a ball of water, it freezes from the outer part and then starts, because of the low temperature, then it starts freezing from the, it gets the shell gets thicker and thicker. What happens then? Okay, what happens to the surface? What happens to the tectonics? How does it break? How does it pop? It's incredible laboratory for the study of how planets work. So, really exciting, and it's been motivating me for decades. We had the Galileo mission, and of course all the Voyager missions, and then New Horizons to Pluto. Who would have thought? Who would have thought in our life?
That was cool. That was money well spent. NASA got its, public affairs budget. Everybody was so fascinated by that Pluto mission. That was really cool. Well, one of the things,
of course, it was none of the above too. None of the above. Like, could it? What'll it be? Ice? Well, it's probably old, and no, it's really active. It has nitrogen glaciers. Anyway, sorry.
Pluto does. Well, so I'm really fascinated in the repetition of patterns at different scales. Like, I'd like to do a talk about this. Looking in the universe, you see galaxies, and you also see the same shape in hurricanes, and you see the same shape in little animals. And there's just lots of things that repeat the pattern. And as you were describing these outer planets, the whole universe is essentially a bunch of matter that rotates around itself, right? Like there's groups of galaxies and solar system. This pattern just repeats itself constantly. That's an interesting thought.
It is, and that may be really fun to talk about. It's something I never really, it's kind of like Mandelbrot and the, you know what I'm saying, and but it'd be really fascinating. Check with the guy I recommended from Harvard too. He could he probably has got a really good perspective on
We'll
that.
talk about that on the next podcast. So
Excellent.
Erica, why? So you got into the program at Brown. Why the outer planets? There's lots of different things you can study in astronomy.
I think there are so many reasons that they're an interesting collection of worlds generally, whether you're interested in trying to find potential places to look for life in the solar system or interested in how the solar system forms. But for me personally, it's just that we can take this one tiny detail about how these worlds work and see how that causes all sorts of changes in how they evolve over time. So one tiny detail, like it being made of ice and that ice being less dense than the liquid water, can change how the stresses that affect all planetary bodies are expressed on the surface. And it leads to these worlds that we know relatively little about, but are so fascinating to study.
Yeah, that's true. The fact that, like, in general, solids are more dense than liquids, right? So a solid something will sink in a liquid whatever, except ice. Is that the only chemical that does that? We wouldn't have life on Earth, right, if it wasn't for that weird property, I think.
I think there are a few other substances that do that, like if you had pure silica,
Right.
it'll do that. But yeah, most of the common rocks we find on Earth and the terrestrial planets are always denser as a solid. And that lets you do really cool things like have cryovolcanism that's driven by freezing. Usually on Earth, we think about melting things to get volcanism. But on these icy worlds, if you have liquid water that's freezing, it can pressurize the water and cause it to erupt in geysers or some volcanic features that look remarkably similar to volcanism we see on Earth or the moon.
I did not know that. So, I mean, it makes sense. Ice will crack your pipes, right? Because it expands. And so that same pressure, if it's on a planetary scale, I call it planetary scale. These are moons that we're talking about, right?
Yes.
But it'll actually cause volcanism. That is so cool. I never knew that.
Yeah, it's exactly the same physics.
So the outer planets are Jupiter, Saturn, Uranus, and Neptune, right?
Yes.
And we're not calling Pluto a planet anymore?
I think there's still some ongoing debate in the community about that, but for the moment, no. But it's a really good point about how we talk about all of these things and what we mean when we say planet.
Yeah, we need to make Pluto great again, I think. I'm going to vote for planetary status.
It's interesting that the debate there was mishandled, really. I think when the debate about the reassignment to actually dwarf planet at that time,
right?
But it was really a testimony to what we've learned, not what we don't know. For example, we discovered hundreds and hundreds and hundreds of Kuiper Belt objects. These are small icy bodies in the outer solar system. We didn't know about it at all. And when you look at the population, Pluto fits much more into those than it does into the planets. So if it had been presented in that way, we have a new class. Look, Pluto fits there. No, we're demoting it. It's no longer a planet.
Yeah, it was all about the branding and the marketing. They needed to hire a New York, Fifth Avenue executive to figure out how to brand that.
Barry, we're talking about scientists here. I think I've told you before that there's one place where Pluto is still legally a planet, okay? And that's in New Mexico, which is the home of Clyde Tombaugh, who was the astronomer who discovered Pluto.
He found Pluto in 1939.
So they were so upset that
Clyde Tombaugh is Mexican or was Mexican.
No.
He just lived there.
New Mexico.
Oh, New Mexico. I think you said Mexico. Okay.
Yes,
yeah. He was New Mexican. That's right. I knew that.
Yeah. So it's legally appropriate there to call it a planet. They passed a state law. Okay.
Well, that's actually pretty funny. So it's like back in the 1800s, some states passed laws that said that pi was 22/7 or something. And, sometimes legislatures do smart things. Anyway, so Erica, there's a mission, I think, or maybe a series of missions to Europa. Is that right? That NASA's contemplating. Can you talk about those?
Yeah, I think right now the main one planned is Europa Clipper, which will be visiting Europa and giving us the closest look ever at its surface, as well as helping us search for potential plumes similar to those that we found on Enceladus with Cassini and a whole host of other really fascinating scientific objectives.
Right. It's an orbiter. It's not going to land on the surface.
Yeah, so it's going to be doing flybys. I know there have been proposals for landers. I'm not exactly sure where those are in the funding stages at this moment.
Right. That's always the question. But thankfully, I think Europa Clipper, there was a congressman here in Houston. I was in his office. John Culberson, I think, was the guy that was really, he made that mission happen. And he was trying to get it on an SLS rocket, and now it's on a Falcon Heavy. Is that right?
That's right.
Yes.
Which means it's way, way, way cheaper and can launch quicker, but it's going to take a lot longer to get there.
I'm not sure.
Something like that. Yeah, we'll worry about that another time. So Europa is a moon of Jupiter. And well, before we dig into the moons, describe outer planets. So Jim, we've been talking about plate tectonics and volcanism and all this stuff, but those 4 gas giant planets are very different than Mars and Venus and stuff. So what's it like? Like if you went to Jupiter, what would it be like?
Well, first of all, they're huge. Okay. I mean, I think a great distinction is Earth-like planets. They're within a third to half the size of the Earth, the ones we've talked about, Mercury, Venus, Earth, Mars. And these are just huge. I mean, you could fit an Earth kind of like a couple of Earths probably in the giant red spot on Jupiter. I mean, they're huge. And so they have this, and they're gas giants, they're gas. So they are solid way, way down, thousands and thousands of kilometers down, because it's just like we were talking about with the state of material, it gets so deep, the pressure of the atmosphere on top of that is so great that it actually compresses hydrogen and it compresses it into a solid.
Hydrogen.
So and so
wow, does that even exist on Earth? Can we make solid hydrogen?
Good question. I don't know whether we can reach those pressures or not. I'm the wrong person to ask. Maybe Erica knows.
I think we can. They're called thermonuclear weapons. I think that's
right. Yeah.
For a microsecond or something, probably. Yeah.
Yeah, probably. Yeah. Good point. So so anyway, so geology, it's not happening
right
in our lifetimes, that's for sure. And so they're really interesting, and they have, again, big magnetic fields oftentimes, sometimes like Neptune, Uranus, rather, they're tilted, on their axis. How did that happen? What's going on there? And
one of them's tilted like 90 degrees, right?
Pretty much.
Yeah.
And then, so all of these key questions, and Juno, which is in orbit around Jupiter right now, is designed to study those various things. And actually, I'll send you to a guy who's the PI on Juno, a really great guy. Got to know him during Galileo years ago when he was a young JPL scientist. Anyway, so they're just completely different. Okay, and they're in a way a little bit more like a star, but they're not luminosity. Luminosity is nowhere near that.
The radiation is a problem too, right? I've heard. Like, is that bad for spaceships? And why is the radiation bad? Because it's so far from the sun. Does Jupiter make its own radiation?
It makes its own radiation, and indeed it is.
Wow.
So in designing the missions, you have to you need to use Jupiter. First of all, with something that massive, it's hard to go into a satellite right next to it. So you need a lot of energy to do that, because you're fighting not just, you're fighting Jupiter's gravity field.
Right.
But you also need to design parabolic orbits, I guess that's the word, that spend most of the time away from Jupiter.
Right.
So that's kind of
because of the radiation.
Because of the radiation damage, and all the spacecraft parts and the software and other kinds of things, it's not good.
What kind of radiation does Jupiter make? I mean, is there fusion going on there like the sun?
I'm not sure. I don't know.
That was something I didn't. Yeah. Do you know, Erica? Is that?
No.
Okay.
It has a magnetic field though, right? I've seen these auroras on Saturn, and the pictures are incredible.
Yeah, it's pretty amazing. It's and the beauty of the atmospheric circulation is just phenomenal. I mean, we were able to watch this in Galileo, and of course it's been known from telescopic observations from Earth for centuries, or well, at least a couple hundred years. That would be centuries, wouldn't it? Yeah, that's good. So it's like it's just an amazing difference, and there's a whole different planetary astronomers who look at atmospheres are kind of a different breed. You know what I mean? And some study the atmospheres of the terrestrial planets, others study the atmospheres of these outer planets, and we're learning a lot. Learning a lot. It's incredible.
It's funny to call them atmospheres because it's actually the planet.
Yeah.
I mean, to a certain extent, you know.
Yeah, that's a good point. That's a good point. I mean, being a geologist, you like to be standing on the ground and looking up at the atmosphere and here.
Right.
Yeah. So the Galileo put a probe into the atmosphere, and which eventually, of course, got crushed because it went into depth. But it made some measurements of the elemental composition of the atmosphere and so on. So it's interesting.
Mm-hmm.
So yeah, very interesting. And again, to us as geologists, it's the satellites. It's all about the satellites.
Right. That's what's really interesting. If humans are ever going to go out there, it'll be to the satellites, not to the planets. But what are these planets made of? Because they all look from the space station. I could tell Jupiter and Saturn because Saturn is yellow and Jupiter is orange. I mean, you can tell with your naked eye, that they're different. So hydrogen, but Uranus and Neptune must be different, right? Because they're blue.
Yeah, they're minor species, and hydrogen, helium, nitrogen. I don't know. Erica, you want to bail me out on this one here?
I can try a little bit. I think, like Jim said, it's minor parts of each of these worlds that are causing the differences in color. But for example, Saturn is a much more water-rich system than Jupiter. And so that's part of the difference and why it's such an icy system in general compared to the satellites we observe. So all of these compositions tie back into what's ultimately forming these moons early in the solar system's history.
Right. But the planets themselves, Jupiter, Saturn, the four gas giants, are made of basically the same stuff, or
at least Jupiter and Saturn. I think there might be some more differences that we still don't know much about for Uranus and Neptune.
Wow.
And I think, Terry, it's sort of like that, our initial view of the solar system, that the temperature pressure distribution in the collapsing solar nebula creates a temperature pressure gradient as you go out. And so, that's why we have so much water, Mercury doesn't. And moving on out, that's the stability of various elements at those ranges of temperature and pressure is going to have an effect on what condenses. So that's a testable hypothesis. It's not like, oh, we know this, here it is, X, Y, Z, this distance, but it's a testable hypothesis for the trends. And so that probably explains it. Like, okay, so Saturn has more water, it's further out, maybe a little bit more stable, and that sort of thing. So yeah, and the rings are fascinating too. That's another unbelievable.
I want to talk about rings. So you've got the planets that are gas, you've got the moons that are rocks, and you've got rings. But back to that point. So, if you have on Earth or anywhere, dense things sink to the bottom and light things rise to the top, right? Excuse me. So was the solar system like that? The dense rocky planets kind of came to the middle and the lightweight gas stayed in the outer parts of the solar system? Is that, or no?
I think it wasn't so much gravity as it was the temperature pressure gradient. So I think the basic concept, Laplacian kind of, is that there's a swirling solar nebula like we see, okay, and then that starts to collapse. So the ring of material starts to decrease, and the central part starts to get hot and form, and then there's a major temperature pressure distribution. So the high temperature stuff, things like water, won't condense there. It goes out, okay? Iron, heavy elements will. So that's why you get mercury, okay?
Right.
Somewhere in the middle, you can get silicates and you can get water. That's the Earth. And then further out, it's, you have enough decrease so that a lot of stuff can condense, and it's the volatiles, okay? And so these things, this swirling nebula, little turbulent eddies set in, and these kind of things form basically, and
formed into planets.
And that's a testable hypothesis, because that's what we're doing with exoplanets right now. And the funny thing to me, not funny, the interesting thing to me, and I love this because it's totally predictable. Our solar system is a little weird, whereas, oh, it's our solar system. They should all look like that because
Right.
it's us, right?
Right.
Anthropocentric, right? Exactly.
Exactly.
Yeah. Anyway, so it's another fascinating aspect of this.
Okay. So you have the planets. They're these big gas balls on the outer edges. I think they're really cold. And then as you go in, they get more dense and super hot and a lot of pressure. But Erica, can you talk about, so the other two things are rings and moons. And by the way, I apologize. My right eye is going crazy. I got some shampoo in it and it's like, I feel like I'm having an allergic reaction to my right eye. So if I'm doing that, that's why I'm doing that. But can you talk about those? What are rings and why are they there? And obviously Saturn has them, but do other planets have them? And then let's talk about the moons.
Yeah, so actually all of the outer planets have rings of some sort. Saturn's are the most extensive, and those are mostly made of water ice. So just these little particles of ice. Sometimes it's small, like millimeter sized particles, especially, there's one of the rings that's actually created by one of satellite's moons erupting icy particles from its south pole. But you can also have these rings made of larger icy chunks and even containing very small, irregularly shaped icy moons. And we would call these irregular moons because they're not these big worlds that, were they in their own orbit, we might call them planets.
Mm-hmm. So the rings around Saturn are in part created by ice volcanoes spewing ice, and that eventually ends up in the ring. Wow.
Yeah. So just imagine this tiny little moon constantly spewing out material, and it's going around Saturn in its orbit and creating a ring as it does so. But
That's
the more
amazing.
massive part of the rings, I don't think we're entirely sure how they got there and when they got there. Saturn's rings could be much younger than the planet itself. So perhaps there was a more massive icy satellite that got disrupted gravitationally, just in this tug of war between Saturn and the other moons in the system.
Are moons always in the same plane? Or, you know what I mean? Like the planets are not in the same plane around the sun. There's a couple degrees of difference. If the sun were on a table, all the planets wouldn't be on the same table. Some of them would be above, some of them would be below the table. Is that true for moons? Are they always in the
I would say that, so even though the planets might vary by a little bit, they're still mostly within this disk of the solar system.
Right.
And for moons, that at least the regular moons, the large ones that are pretty spherical, that's true. Some of the very smaller ones are in different orbits, and that might be because they were captured.
Right.
How
do you capture something? So when you fly the space shuttle, when you get to the top of your orbit, if you don't do a burn, you're going to fall back down to where you were, right? So if you're a moon flying by Jupiter, unless it does a burn, unless it has some type of force on it, it's just going to go back to where it was, right? So how does that happen? Does it run into another moon?
It's really just getting pulled in by the gravitational force of the planet. So as it's going by, rather than continuing on its way, it'll start falling towards the larger planet. Right. And depending on what speed it's going at, it can either get pulled in entirely, like we sometimes see comets crashing into these giant planets,
right.
Or it's going to get trapped in an orbit around it. And that's where we might see some of these irregular moons coming in. That's
a good point. There was one, I remember, I don't know, was it 10 or 20 years ago on Jupiter? There was like multiple big giant, it had like, bruises from this impact.
It was when the Shoemaker-Levy comet hit.
Right.
Yeah, we photographed that with the Galileo. That was exciting time.
Yeah, that was so cool. Okay, so what are the rings like? Like there was a movie, Ad Astra, don't recommend it, but it was really cool to see the visualization of Neptune, I think is where Brad Pitt went out to Neptune to meet his angry father, and they had a fight. But it was really cool to see that visualized. But like, if I were in a spacesuit floating around, would it just be small pebbles, or would it be super thin, or is it like a football? What is it like in the rings?
They're really thin. So if you were looking at them edge on, it would be similar to looking at the edge of a sheet of paper.
Right.
But if you get close up, then you're looking at these many different icy particles of all different sizes.
Right.
And there's some space between them, and even patterns of gaps that are created by smaller moons within the rings.
So if you flew a spaceship through the rings of Saturn, you would get a bunch of dents from hitting these ice particles.
I think it depends where in the rings you are, but there are
Right.
some parts, yeah, where you'd want to worry about that.
Yeah, like the Cassini division. Can you talk about that? Because there's divisions in the rings, right? It's not like one continuous thing.
Yeah, I think this is really cool because it really shows you this mini solar system perspective that Jim was alluding to earlier, where a lot of these gaps are created by moons clearing the orbit. So if you're a small ice particle and you're going around Saturn pretty slowly and this larger moon comes by, you're going to get swept up into its orbit. And so you get these gaps where everything that was that close to the moon has fallen into the moon, and everything further away remains. And that's how you get these different rings around Saturn with the gaps between them.
Right. So if the ring is, I don't know, they used to have those frisbees that were like rings, with a big hole. If that's Saturn's ring, it's actually not a solid frisbee. There's a big gap in there. So is there a moon hanging out there, or did it just pass through a million years ago and this is what's left over?
Most of those gaps are where we see moons today.
Right.
Yes. So.
Okay. Well, let's talk about, so speaking of moons, what are the coolest moons out there? So really Earth has the moon. Mars has two weird moons that are not, there's not much, they're like asteroids that got captured or something. And then the outer planet moons are really cool. So can you just talk about them? Yeah.
It's very hard to pick favorites because they're all so interesting. And I really want to stress that these worlds are like mini planets. So Ganymede, which is a moon of Jupiter, and Titan, which is a moon of Saturn, are larger than the planet Mercury.
Oh, wow.
And they have such a diversity of different features. So these are really planets within their own rights, with all the geologic mysteries of a place like Mars or the moon or Venus, where we can really dive into all the complexity. I'd have to say among my personal favorites is Enceladus, a very small moon of Saturn that has these large cryovolcanic jets erupting from its south polar terrain.
Wow. All right. Well, let's start with Jupiter. So there's the Galilean moons. And if you have a small telescope or binoculars and you look at Jupiter, you can see, normally you only see three because one of them is in front or behind the planet, but you can see the four going around. What's interesting, when the Brits started when everybody was exploring back in the 1600s, that's how they measured their longitude. They had the Farmer's Almanac of when the different moons would cross Jupiter, and that's how they could they didn't have good watches like we have now, like my trusty Omega, and they would actually time when the moon, and then they would set their time, and that's how they could figure out what their longitude was. So that was pretty cool. And I'm guessing that was part of the reason why Galileo figured out that we're not at the center of the universe. And then I assume if you see these other planets orbiting around a planet, then that probably made him think. And then he got in trouble with the church, but that's a different story.
Yeah. So
the four Galilean moons, can you talk about those?
Absolutely. Unless Jim, if you want to start on this.
No, good.
So the Galilean moons are fascinating because we see this transition from a completely rocky world like Io that Jim was talking about earlier to Europa, which is a mostly rocky world with a very thin icy layer. So Europa is 95% rock, we think, and just has this thin icy shell that's very active and is covered by fractures and all of these really unique features like pits and chaos terrain that we're still learning about how it forms. And as we go further and further out, we get to icier worlds that are less geologically active, but still tell really incredible stories about the history of the Jupiter system. So we have Ganymede, which is mostly covered by an incredibly old, dark terrain, but about, I always forget whether it's 1/3 light terrain, 2/3 dark terrain, or the other way around. But much of its surface is covered by this brighter terrain that formed about 2 billion years later, which means that something happened to Ganymede that gave it the energy to have all of this resurfacing, and whether that was through a process of spreading, like we might see more similar to Earth, or large flood volcanism, like I think Jim talked about on the moon in a previous episode.
Mm-hmm. Do any of those moons have plate tectonics?
I think it would depend on who you ask and how they define plate tectonics. But Europa probably becomes the closest because it has these fractures and bands that we see spreading apart.
Right.
The question is, can you really subduct them under each other? Because the ice is lighter than the water, so it doesn't want to sink down underneath it, like a plate on Earth would want to sink down.
Right.
Yeah, that's a really good question, Terry. I think, one of my ex-postdocs, Bob Papalardo, who's actually the chief scientist on the Europa mission, the Europa Clipper mission, and former student, Louise Proctor, they published a paper which said they were crustal spreading. And the problem has always been, well, where are the mountain belts? Where is the convergence?
Where are the Rocky Mountains, right?
Exactly. And they made the point that it's probably, because it's ice, it's probably ductile deformation. So we might be looking at differences in crustal thickness. So, you're separating it and then you're squeezing it together in another area, and it just thickens the crust a little bit, and then maybe it equilibrates, et cetera. So their idea is that we shouldn't necessarily see these. And with Europa Clipper, we may be able to see the variation in the crustal thickness, to look at topography better and see if there are any rises and things like that that might reflect it. So it's really an exciting question. And again, it gets back to this question of, wait, you can't just think about the way things work on Earth. You got to realize that there's different kinds of deformation with different materials, and they should give different geological signals. So that's another mystery that hopefully Europa Clipper will help to understand.
So Europa is probably the most interesting. It's definitely one of the most interesting because it might have life because of all this water, right? I mean, I don't know if it has life or not, but of all the candidates that we know of, Europa's on the Mount Rushmore probably of potential life candidates, right?
Yeah, I would say so. Europa and Enceladus both have liquid water oceans, and they are probably an ocean that's in contact with the rocky part of the planet. So it's really important when you're thinking about the ingredients that go into developing life to have water, we think, because all of the life on Earth that we know depends on water.
Right.
As well as you need energy for that life, and you need the right chemistry. So on Earth, that's commonly carbon, hydrogen, oxygen, nitrogen, and phosphorus. And a lot of those ingredients you can really only find in the rocky parts of these planets. So you need all of the parts, the water, the energy, and the ingredients all in the same place for a long enough amount of time for life to develop.
Right.
And it seems like Europa and Enceladus might be places where this happens.
On the surface, you're going to have a lot of radiation from Jupiter, and there's no atmosphere, right? So but the water is going to protect them from that radiation. So that would be another.
Yeah, the question of where on Europa or Enceladus to look for life is a really good question. And I think a lot of people would say that you might need to go to the subsurface, right? At the underside of that ice shell to really find the most life. But there's a chance, especially if there's cryovolcanism bringing up fresh material from the subsurface, that you could look for life on the surface of these worlds as well.
How thick is that ice crust?
Depending on where you I was going to say, it depends a little bit on where you go, but tens of kilometers for Europa.
So it's funny to hear you say, it's just this thin little ice thing. Well, you could say that Earth has just a thin little layer of water. It's mostly rock. But if you're on Earth and you're on the ocean, it doesn't seem that way, So an astronaut on Europa would be overwhelmed with a sense of, this is a giant ice. There's unlimited ice in all directions, and it looks pretty dangerous too. All those cracks and stuff. It doesn't look like a safe place to land.
It is a problem, Terry, because in fact, at the sub, people are thinking about also snow pinnacles, ice pinnacles too, at the scale we can't see yet. So that's one of the reasons Europa Clipper will give us more data, high resolution images to actually look at what's going on. Another interesting part about Europa is that the surface is like about 40 million. It's with a few tens of millions of years old. Wait a minute, how's that work? How come there are not very many craters? Okay, and it's funny. A quick story: as I was with the Galileo images, they're just incredible. I was flying back from NASA headquarters to Providence and sitting on a plane, working away. I had all these images. I was doing maps and stuff. This guy next to me says, where is that? Is that ice? That's where is it? Europa. Where's that? Turns out this guy was a admiral at the Naval War College, and he taught a course in exploring subarctic exploration.
Yeah.
And so we really hit it off, and I made up an exercise for his class to make up vehicles to explore Europa, submarine vehicles to explore Europa. It was just one of those classic kind of things, you know what I mean?
Yeah, they're there in Rhode Island, right? The Naval War College is right there.
Newport,
Yeah. Well, the idea that I've heard of, Eric, is that you could put maybe an RTG, a nuclear piece of metal that's hot, and it would just melt its way through the ice. Like that would be a long drill bit to send to Jupiter to drill 10 kilometers through ice. So is that how we would get it down in the ocean?
That's definitely one way you could. The other place is to look for places where the ocean comes to you and take advantage of that. So if there are large crevasses on Europa, like we find on Enceladus, you might be able to send robotic explorers down into those crevasses and then have them sort of crawl along that boundary of the ice and the ocean.
That would be amazing. That would be so cool. But how is it going to communicate? You can't send radio signals through water, right?
Yeah, a lot of the designs I've seen are for tethered vehicles.
Okay.
And I think a lot of the testing that people have done on Earth for these have been where they send it under ice shelves in the Arctic or Antarctica and just communicate via tether to these vehicles.
Right. I hope we can do that. Of all the things that NASA does, that's funding that's definitely worth, I think, exploring Europa. So you either have rocky or icy moons. Do any of them have atmospheres to speak of?
Absolutely. So Titan, one of the moons of Saturn, has a nitrogen-rich atmosphere that's actually about 1.5 times the pressure of Earth. So it's a lot denser, and the gravity is a lot less on Titan compared to Earth. So it's the perfect place for a rotorcraft to fly around. And that's exactly what the Dragonfly mission will be doing in the mid-2030s. But we've actually descended.
So we're going to send, we're sending a helicopter to Titan.
Absolutely.
Wow.
Yes.
That is very cool.
And this is following on the work of Cassini, which had to use radar to look through this atmosphere and see the surface. But it's actually the only icy moon that we've ever really landed on. So the Huygens lander, which was part of the Cassini mission, descended through Titan's atmosphere and landed on the surface. And what it saw there was what could have been a riverbed here on Earth with all of these rounded stones. But rather than being made of rock, these stones are actually made of ice. And rather than water carving all of the channels that we observe on Titan, it's much more likely it's liquid methane and ethane there. And there's even a whole methane cycle, just like we have the water cycle on Earth, where there's rain and it washes through channels and gets evaporated up into the atmosphere.
Wow. Methane and ethane is rocket fuel, potentially.
Yes.
That's what I'm thinking. But there's no oxygen. If there was oxygen, there would be a big fire, right? So that is amazing. Yeah.
It's thought though that this might be an analog for early Earth atmospheric properties, et cetera. Okay, so it's kind of it could be like a primitive atmosphere that was like the Earth. So that's another reason people are really interested. How would that work and so on? Not necessarily with methane and ethane, rivers and things, but just a general composition and how that evolves early on. So
that's pretty cold there, right? Titan is.
Yeah, it's probably anywhere from about 70 to 100 Kelvin, or a couple, maybe about 100 below Celsius freezing.
Right. So that's chilly. That would be an amazing place to send people to be in this nitrogen atmosphere with methane rivers. That is really cool. Are we going back? Well, you said we're going to fly a helicopter in the atmosphere. Will it be a lander or just a helicopter?
Yeah, it's going to land, do science,
Okay.
fly, and it's doing science all the time as it
Right.
flies to these different sites, but it'll be essentially hopping around Titan on these flights, and it'll traverse kilometers of the surface.
How's it powered?
I believe it's an RTG. I'm not 100% certain.
Nuclear powered, yeah.
The other proposal that was in competition with this one was for a boat to go into the seas. Okay, but the helicopter made the cut.
The Air Force One over the Navy.
Yeah, exactly.
The seas. So it's actually, there's significant liquid ocean on Titan.
Yeah, at its northern pole, we actually see these huge seas. And there are some basins in the South Pole that suggest that at different times in its history, those have actually been full of liquid methane and ethane as well.
That's crazy.
Yeah, we think there's seas and even a groundwater network, although of course it's not water in this case.
So when you go out to the really outer planets, I think Triton is one of the moons. Are there any interesting moons out there that you're starting to get pretty, I mean, Jupiter and Saturn are freezing cold, but it's even colder the farther out you go, right?
Yeah, the further out you go, the colder it gets. And more materials that we would think of as gases or liquids further in the solar system start to condense and become solid. And that's where you see these nitrogen glaciers on Pluto, or some of the ices on Triton that we think might be nitrogen forming an ice cap over water ice that makes up its hard surface.
And also Erica has been doing experiments in the laboratory, taking ice spheres and freezing them and watching them freeze from the outside in, and then watch the cracks develop to see if there are patterns like Europa. Tell them about that. It's really fantastic. And then the end member too, what happens at the end.
Yeah, so like we were talking about earlier, where when you have water freezing in a pipe and it explodes, and that being similar to how icy worlds can freeze and pressurize and have that cause cryovolcanism, that means we can simulate a lot of the physics responsible for this cryovolcanism right here on Earth in the lab. And so part of what I do is I fill up small spherical containers, which are actually Christmas ornaments, full of water, and I put them in a nitrogen-cooled freezing chamber to freeze them at temperatures ranging from -15 to -70 degrees Celsius. And I watch as that ice shell forms from the outside in, and it's freezing. And the only place that ice, as it's expanding, can go is inside. And so that causes the pressure to build up until it's too much for the ice shell to take, and the ice shell cracks, releases some liquid, releases that pressure, and then it's freezing all over again because it's still in that very cold environment.
Right.
And so you see just fractures appearing over and over again with the pressurization, until eventually the stress is so great on the ice shell that it completely breaks apart in our experiments. And so what we're trying to do now with numerical models is figure out how we scale that up to the icy worlds.
That's amazing. So you can you analyze the way the cracks are, and then I guess, that's what you just said you're trying to do. You can model the cracks that you see on this Christmas ornament and predict what would happen. And you're not done yet. Do you think your models are going to match,
I think that although you probably won't see an exact match because these are really complicated places,
right,
you can already learn some very basic things. So one thing we learned in the experiments is that depending on how much gas is in the water when you freeze it, it changes how compressible the water is. So how quickly it can build up pressure, how squishy it is. And that means that for freezing something the same amount of time and freezing the same thickness of an ice shell, just based on whether there's a little bit more gas in the water, you could have half as many fractures form. And so maybe just by looking at the surface of these worlds and understanding when the fractures formed, we might be able to tell something about the composition of their oceans.
Well, if you were going to design a human mission there, what moons would you want to go visit with people?
Oh, that's a really good question. I think with people, I'd be most excited to visit the moons that we think are the most likely candidates for life. If you can get around the planetary protection issues, I think just the ability to go target samples and target the deposits that you think are most likely to preserve evidence of that would be a really valuable mission.
So the planetary protection, meaning not protecting Earth from these moons, but protecting the moons from human germs that could turn into life. I mean, we're all spewing bacteria and DNA constantly, right? So
yeah, just like we worry about that for Mars, we have to also worry about it in these environments that we think might be hospitable to life on their own. So if it's not there, and especially if it is, we really don't want to be getting in the way of that.
Right.
And you're right, Terry, that this is what I always tell the people who are worried about human exploration of Mars, that look, the first human that sets foot on Mars, it's a Noah's Ark of microorganisms. That's it.
Right.
That's it. Yeah.
So I wonder if the overall trend in society is to be more sensitive and not offend anybody. And that's kind of the ultimate offensive thing, right? To plant our DNA in another planet. I wonder if that'll ever even be allowed. I mean, we're a long way from sending people to Mars, the reality, but I wonder, can you see scientists just stopping that from even happening?
I think it's possible. I mean, it's very difficult to predict the future because all evolution is nonlinear.
Right.
And, but if we continue on this curve of being much more aware about what we do to the environment and our place in the environment, I think that's a really, really important question to ask. And we're facing that right now with Elon Musk's plan to, we're talking about working with him to think about, okay, where's the ice? What's going on? How are we going to support it? And that's going to come sooner rather than later, actually. So that is having to answer that question.
Right.
And I think
it's a question. No one talks about it really publicly. I haven't heard, but it's one that needs to be addressed.
Well, there are committees. Committee on Space Research, an international committee, has a panel on that, and they study it all the time, and they debate. And then NASA has a planetary protection officer.
Right.
I've always wanted her badge, but
so that's not asteroid defense. There's also an asteroid defense.
That's a separate topic. That's having something come in and terminate life as we know it on the Earth, more or less. Yeah. Ask the dinosaurs about that one.
Don't Look Up. Did you guys see Don't Look Up?
Yeah.
Did you like it?
Yeah, I really did.
I love that movie. It's not, I mean, it's about climate change, obviously, but there's much more. There's a lot of issues in the world where something's really obvious and some large segment of the population doesn't believe it. And it's about a lot more than just climate change, I think. I like the premise of it.
Yeah, it had a lot of really great themes about how we communicate what we know and, more importantly, what we don't know.
I changed my Twitter heading years ago, and it said, in God I trust, everybody else has to bring data. And I stole that from the Houston Astros. Their general manager had that on the wall, like, Moneyball. That was their headline. But it was what I was saying is pretty profound. Like, I don't believe science at all. I know science, or I don't know science. It's not a belief, it's knowledge. And there's a difference between that. And I think we need to make that distinction. That's a role that you guys have as I'm not a scientist. I'm just a old fighter pilot, but promoting, actual facts, and let's do a hypothesis. And we don't know this stuff, and we'll be honest about what we don't know. And
I think it's really, really critical. And, I mean, people talk about, oh, well, we're seeing a convergence of religion and science. And, to me, I hate to be blunt about this, but I think it's important to make the distinction. Mm-hmm. I see that as a fight to the death, because if you adopt things on faith and science, you're not a scientist. And virtually everything that we believe in religion is based on faith.
Right.
And that's a different way of saying what you already said, which is that, bring me the data. Okay. And I think that's the problem. Is now we have politicians who across the world who are being deified. Oh, well, they lie every minute of the day, and people believe it. And that's one of the science has been one of the casualties of that kind of new trend, so to speak.
New world Brave New World. I have that book. I just ordered the book. I've never read it. I was the worst English student in the history of high school students. I never read any books, and I apologize to my English teachers whenever I can. But that's a book that I'm going to read now because we're entering that phase of life. Before we started the podcast, Jim, you and I were talking about that. Yeah, it's an interesting thing. Isaac Asimov. I used to like science fiction when I was a kid, and he wrote a book. It was basically behavioral science. What was that? Was that trilogy, Foundation and Trilogy, where you could predict the course of history of a civilization through this behavioral science. It was like numerical psychology. It's an interesting concept, but I kind of feel like we can analyze our own civilizations here because we need more scientific method. We need more Ericas and out there, telling these cool stories. And you can use the same method that you're using, Erica, to study icy moons of the outer planets. You can use to like make basic decisions in your life here on Earth about a lot of things. So
have you read Collapse by Jared Diamond?
No, what's it called?
Collapse. Yeah, I can send you that. It's exactly what you're talking about. It basically traces the history of various, not quite civilizations, but sub-civilizations, ethnic groups that evolve in certain ways in different parts of the world, and shows all the reasons they didn't make it. Okay.
Right.
It's exactly what you're saying. I mean, Easter Island, they built all those idols and nobody knew how to fish. And they cut all the trees down to move these things, etc. And then they perished partly because they couldn't support themselves. They didn't have an alternative. It's just filled with stories like that. It's absolutely fantastic, fascinating. Anyway,
I will read that book. That sounds really good. How about you, Eric? What do you? Well, you're a PhD student, so you probably don't have a lot of time to read for fun. You're reading science,
but I do love science fiction, and I've mostly focused on, I think, probably ones that are a little bit outside of the solar system. But
what's your favorite science fiction book?
Probably Contact by Carl Sagan. That was one of the first bits of sci-fi I got into, and still a special one to me. But I really like how it shows you science and society interacting on this really fantastical premise, which is the discovery of alien life communicating with Earth. But I think it just really captures so well a lot of the reasons why so many of us get into science. It's just this drive to discover what we don't know and to always learn more.
It's funny. I actually have not read Contact or seen the movie, and I've been writing a lot, and I just started writing this story. And it was the Contact story. I shared it with someone, and they're like, "Dude, have you seen Contact?" And I was like, "No." They said, "That's Contact." So I started to write that on my own. I didn't even know that.
Terry, Carl Sagan, one of the things we lack today is really efficient and exciting communicators in science. And Carl was absolutely that. I mean, incredible. Plus being a really good guy. I mean, incredible. And you're filling this role here by asking the questions you're asking. You say, I have no science background, but you have an intellect and a interest and capacity and excitement about this. Okay. And so that's the most important thing. And then, you talk to authoritative people, some of them, cut me out of that, but you're really performing a wonderful service there in that context. So thanks.
Well, it's fun. I love this subject, and I have all different kind of people on the program, but I think our listeners like space for some obvious reasons. And so these are really cool discussions we've had. So we've actually gone through all the planets now. We touched on the Kuiper Belt. We didn't talk much about them. They're these icy objects. So there's a Kuiper Belt, which are icy objects out past Pluto. And then there's the Oort cloud. Can you talk about the difference between those?
Yeah, so the difference is really where they're located and the shape. So the Kuiper Belt is a disk, just like how our solar system falls on this general disk. Okay. And it's objects that are, with a few degrees of freedom within the plane of the solar system, and they're out past Neptune. But then if you go even further out, you get to this spherical shell of objects. So it's no longer a disk. We're talking about just this entire encircling zone of the solar system. that are filled with what we would call comets when they come into the inner solar system.
So the Oort cloud is like the comet factory.
Yes.
And what knocks the comets out? Stars that float by?
Yeah, so it's the distant passage of stars and distant supernova that can just like slightly perturb these objects. They're really small, but once you give them a slight kick towards the inner solar system, they're coming towards the sun.
They're falling in. Yeah.
And the beauty of those, Terry, is that, if you think about the same temperature pressure distribution in the collapsing solar nebula at the beginning, okay, these are things that are way out there and they have been essentially unmodified compared to Earth and everything else.
Mm-hmm.
So when they come in, it's like, whoa, here's a piece of the starting conditions. That's really a miracle. You know what I mean?
Right.
So that's one of the major reasons that they're so fundamentally of interest.
And we've sent missions to comets, right? To go fly through the tail and measure what's in there.
And landed on them, too.
Yeah.
Europeans. Yeah.
Oh, that's right. Hayabusa, the jet.
I think that was to an asteroid.
That was an asteroid. Okay.
But the Rosetta
What's the difference between a
mission,
comet and asteroid? Sorry.
So the difference between a comet and an asteroid has to do with where they're found and what they're made of. So asteroids tend to be rockier and they're found in the asteroid belt between Mars and Jupiter.
Yeah.
And then comets are coming from the Oort cloud or a family of comets near Jupiter. So they can come from a couple different places, but they're icy objects predominantly. So they're almost entirely made of ice with small rocky components.
Water ice.
Yes.
So the asteroid belt, Jim, we might have talked about this. I can't remember. Was that a planet that got exploded or something? Was it like the Death Star that blew up? Or
that was an early hypothesis. I think now it's generally considered that basically the tidal interaction of Jupiter grew big early on, and so that area in there is it is the resonances, the tidal resonances make it difficult for a planet to come together. So it's almost like pieces of undeveloped planets, basically.
okay.
Yeah. So
It's a failed planet. Because isn't there a mathematical ratio or pattern of the distance from the sun? Mercury, Venus, Earth. I remember as a kid, I learned that there's some pattern, and where the asteroid belt falls into this.
Yeah, I think
pattern.
that's about right. I lost lock on the name of that relationship. I think it's pretty fundamental. But yeah, Erica, do you have some elaboration on that or correction, if you will?
I think you've covered it. Nowadays we think that the asteroid belt is these leftover pieces of solar system formation, and that's why so many missions have targeted especially these rubble pile asteroids that are just conglomerates of materials that were left over from the early solar system as we try to uncover what got us all started.
Some companies, and many of them I think are based in Luxembourg. Luxembourg seems to be the asteroid mining company. I mean, there's talk of mining asteroids, right? Because there's so much valuable material there. Is that right? Like, why would you want to mine an asteroid? Do you know what the materials are that they're looking at?
There's some, some of them are very dense and they have like metals and platinum group metals and things like that potentially. So I think that's the kind of thing people are interested in. And, that I would say those are the main ones. I'm not sure. Erica, any thoughts on that?
I think there are also some people who consider water as a resource for the same reasons that people are interested in it on the moon and Mars, if you want to use it potentially for fuel.
You could use it for water or rocket fuel. Hydrogen and oxygen is rocket fuel, or oxygen you can breathe. Yeah, water is very useful for what we need in space. Well, so Erica, one final question. What's the craziest moon out there? Like what's one that scientists scratch their heads over? How the heck did that happen?
I think a great example of this is one of Uranus's moons, Miranda, which has these sort of checkmark shaped features and oval features that are just this bookshelf faulting. And we don't really know how those corona formed. I know there's a lot of talk about corona these days, but these are crown shaped features on Miranda, the small moon of Uranus. And this includes cliffs that are 20 kilometers high. And we don't have a great sense of how it formed.
Cliffs that are 20 kilometers high.
Yeah.
That's 60,000 feet.
I will trust your math.
Yeah, that's high.
Yeah, it's really just remarkable features. And part
Wow.
of the mystery is that we've actually only taken pictures of less than half of the surface of the moons of Uranus. So more than half of
Oh,
these
wow.
worlds are a complete mystery to us. We're quite literally in the dark. I
We
mean,
don't know what they look like because you can't get pictures from Earth, right?
yeah. So when
Yeah.
Voyager 2 flew by the system, only the southern hemispheres were illuminated at the time. And we
Mhm.
haven't been back since. So you can imagine how much the quality of imaging we can do has improved in the
Oh, yeah.
past 40 years. It would be incredible to take another look at these and try to figure out what's waiting for us.
And in addition, the James Webb Space Telescope is going to be targeting the outer planets, so that'll be interesting. You might ask your colleague from Harvard there, about that. So that'll come up in the not too distant future, actually.
Right. That's interesting. How do you know off the top of your head how much is Europa Clipper? How much is that mission?
I don't. I've lost luck, actually. I'm not sure.
Yeah, like $1 billion or something.
Certainly many hundreds of millions, but I don't know that.
For the cost of a Falcon Heavy launch and a common bus, we could be sending missions to each of the outer planets every year, for a fraction of what we spend on SLS development. I know you guys aren't allowed to say that, but I can say it because I'm not at the agency anymore. I wish we would. I really do wish we would do more of this planetary exploration because it's so cool. What's the moon that looks like the Death Star? There's a moon with a giant crater or whatever. Which one is that?
That's Mimas. It's a moon of Saturn.
Yeah. I mean, I wonder if George Lucas got Star Wars came out before Voyager had those pictures.
I think so. That's all before my time. So I'll defer to you two.
It did. Yeah. Thanks for reminding us. Well, anyway, so for the listeners, they need to Google Mimas and Miranda.
Yes.
And what about the one, Erica, with the black belt around the equator?
Oh yeah, if you're interested in another really fascinating moon, you can take a look at Iapetus, which is walnut shaped. So it's a little bit flatter than a sphere. And it has this ridge that goes around the equator that's 13 kilometers high in some places. So we're talking about some really tall peaks, and it's just this little ring around the planet. And we're not sure exactly how it formed.
That's amazing. There's a moon with this crazy belt around it that we don't know how it formed.
Absolutely.
Yes.
See, we need to send more missions out there.
Good thinking,
I completely
Terry.
agree.
Yeah, we need to send more missions out there.
Terry, you're in Houston, so how about being the next administrator of NASA?
Yeah, the people in Houston would not be happy about that, but I think the American taxpayer would. That's real value. That when you see these pictures, it's just so cool. The head engineer at JPL, I think his name is Tien Nguyen, is a Vietnamese name. He has the coolest LinkedIn. If you're on LinkedIn, follow him. Every day he posts pictures, and a lot of Juno images are some of the ones he posts. And it's really cool getting the picture of the day on his LinkedIn thing. So, well, anyway, guys, I know this has been a long time, but I really appreciate it. The outer planets are super fascinating, and maybe someday we can send people out there. That would be great. And hopefully we don't find crazy Tommy Lee Jones out there trying to kill Brad Pitt or whatever happened in that Astra. But it's an interesting place, and it tells us a lot about solar systems. And I think we could probably learn about other solar systems, right? Is this true, by just studying the outer planets and their moons?
No, absolutely. I think, yeah. So this is the thing. I told you before when we had our talk about the inner solar system that my exoplanet colleagues are coming to us and saying, "Well, wait a minute. How does this work here?" And so, literally, we had a conference, exoplanets in our backyard. Bingo. Okay, that's your answer right there. Absolutely. Yeah. We're entering a new era of collaboration between planetary scientists and planetary astronomers, and astronomers in general, written larger, okay, which are the ones who are doing the exoplanets. And so, we kind of went where, it used to be that our planet system were astronomical objects. because you didn't know anything about them. But then they became geological objects over the last 40 years because we landed, we sent people there, we explored, they became geological objects. And astronomers went on to look deeper in the solar system and beyond, okay? And so now it's coming back together because we now have a very common interest here. We can tell them something about how the planets formed. They can tell us about the diversity out there. And
Right.
together, it's just going to be fantastic. We're already working on that. It's just fantastic.
Yeah. Amazing. Well, I'm going to go Google these moons and look at these pictures. And thank you guys both so much. And again, if you love Down to Earth with Terry Virts, please subscribe and give us a rating.